Have you ever wondered why your pet cat lives for 15 years while a Greenland shark can cruise the ocean for over 4 centuries? Why we see wrinkles in the mirror while the hydra shows no signs of aging at all? What if I told you that aging is not an inevitable law of nature, but merely a complex bug in our organism's software that humanity is already learning how to fix? Today, we will explore where exactly our biological timer is located, how zombie cells work, and whether we can turn aging from an inescapable sentence into a solvable engineering challenge. Block 1. Why do we age at all? Entropy and the accumulation of junk. Our body is a miracle of biological engineering, but it remains subject to the second law of thermodynamics, entropy. Throughout our lives, metabolic waste products accumulate in our cells that cannot be fully processed. This is molecular junk, damaged proteins, oxidized lipids, and DNA fragments that clutter the intercellular space and the cytoplasm. Imagine a city where trash collection has stopped. At first, it becomes simply uncomfortable. Then services fail, and eventually, transportation grinds to a halt. In our cells, the garbage collectors are lysosomes, specialized organelles that digest waste. With age, their activity declines. This process is known as proteostasis, the loss of control over protein quality. When proteins fold incorrectly, they clump into toxic plaques. Aging is, essentially, the gradual loss of the body's ability to clean house and repair itself. The Hayflick limit and the drama of telomeres. In 1961, Leonard Hayflick discovered that human cells can divide only a limited number of times, roughly 50 to 70. This is known
Initiating
as the
the
Hayflick
replication
limit.
sequence.
The reason lies in telomeres,
Process
the
error.
end caps of our chromosomes.
Limit reached.
Imagine them like the plastic tips on shoelaces. They protect DNA from fraying during replication. With each cell division, telomeres shorten slightly. This is a built-in copy counter. When telomeres are exhausted, the cell realizes its DNA is at risk and triggers a program of cellular senescence. The cell doesn't die, but it stops functioning correctly. It turns into a senescent cell, a zombie cell. These zombies don't perform useful tasks. Instead, they secrete pro-inflammatory factors that poison surrounding tissues. This leads to chronic systemic inflammation, which scientists call inflammaging, the primary driver of age-related diseases. The evolutionary trade-off and the disposable soma. Why didn't evolution make us eternal? According to Thomas Kirkwood's disposable soma theory, the body always has a limited energy budget. It must choose. Either invest energy in flawless cellular regeneration or in reproduction and survival in a dangerous environment. Evolution is profoundly indifferent to what happens to you at 60 if you have already passed on your genes at 20. Therefore, in the genetic contract, nature invests in body repairs just enough to get us through our reproductive years. Mechanisms for cancer prevention or deep tissue regeneration after 40 or 50 become secondary to evolution. Aging is not nature's goal. It is a side effect of the fact that the organism ceases to be a priority for biological survival once its reproductive duty is fulfilled. Block 2. Hacking the system. How future technologies work. Senolytics. Hunting the zombies. Today, medicine is shifting from fighting symptoms to fighting root causes. Senolytics are a class of drugs that selectively identify and destroy those senescent cells without harming healthy ones. Studies on mice have shown stunning results. Removing zombie cells doesn't just extend life. It literally restores the animal's mobility, fur density, and cognitive abilities. This is like updating the software in an old operating system by deleting the corrupted files that cause system crashes. Clinical trials on humans are currently underway. If they prove effective, we will have the tools to cleanse tissues of accumulated age-related damage, marking the dawn of a new era in treating arthritis, cardiovascular disease, and even neurodegeneration. Yamanaka factors, the reset button. In 2006, Shinya Yamanaka achieved a breakthrough. He proved that any adult cell could be turned back into an induced pluripotent stem cell. He did this using a cocktail of 4 genes now known as Yamanaka factors. These genes allow us to erase the epigenetic marks of aging and return the cell to an embryonic state. Today, scientists are experimenting with partial reprogramming, If you apply these genes just enough, the cell rejuvenates but doesn't lose its specialization function. This is the most ambitious project in science, the ability to literally rewind a cell's biological clock. Recent experiments successfully restored vision in old mice by reprogramming their retinal cells. This is proof that aging is not an irreversible process, but a condition that can be managed. Epigenetic regulation and metabolism. We are beginning to understand that aging isn't just about breaks in the DNA, but also breaks in the instruction manual on how to read it. Epigenetics determines which genes are turned on and which are turned off. Over time, this epigenetic landscape degrades and genes start activating randomly. Technologies like sirtuin activation or mimicking the effects of fasting through specific amino acid restriction allow cells to enter a repair mode. When the body senses a nutrient deficit, it triggers autophagy, a process where the cell begins to eat its own defective junk. We are learning to control these switches so the body repairs itself, simulating the conditions under which our ancestors evolved over millions of years. Block 3. The future. Life beyond the limit. New medicine and the concept of health span. It is crucial to distinguish between lifespan and health span. The goal of modern gerontology is to ensure that a person remains active, sharp-minded, and healthy until the very end without spending decades fading away in hospital beds. In the future, medicine will be personalized and preventive. We will monitor our biological markers in real time. If an algorithm detects that inflammation levels are rising, it will suggest a dietary adjustment or a short course of senolytics. We will stop treating diseases once they have emerged. We will prevent them by maintaining the body's homeostasis at an optimal level. Overcoming limits via gene therapy. CRISPR and genome editing are opening doors to correcting fundamental errors. We will be able to enhance natural DNA repair mechanisms, improve the performance of mitochondria, and even modify genes to reduce susceptibility to Alzheimer's or Parkinson's. We are on the verge of transitioning from biological determinism, where our genes dictate our fate, to biological design, where we control our own health. Of course, ethical questions will arise. How do we make these technologies accessible to everyone, rather than just the privileged few? These are no longer scientific questions, but societal ones, and we should start preparing for them now. Returning to the beginning, returning to the question we started with, can we outsmart the biological timer? The answer is, we have already begun. We have stopped viewing aging as a mysterious, inexorable fate and have begun to see it as the sum of specific biological malfunctions. And as science takes steps toward making old age an option rather than a sentence, the main question for us becomes if we can truly extend our vitality for 2, 3, or even 4 times longer, are we prepared to rethink the very meaning of human life, where time ceases to be a scarce resource and becomes a space for infinite development?